This is problem 811E, page 443. For this problem, compute the shearing stress at the horizontal neutral axis for a beam having the cross-sectional shape shown in the given figure for the given shearing force. Use the general shear formula. So they give us a cross-section that looks like this. Okay, and the dimensions are 6 inches on the top, 8 inches on the height, the overall height, and the typical thickness is 1 inch all the way around. Now, they asked us for, move this down, they asked us for the shear stress at the center of the centroid axis, okay? Why would they ask us for the shear there? That's where it's going to be maximum, right? How do we know it's going to be maximum there? Well, look at the overall thickness. Do you see what the thickness would be? It's from here to here plus from here to here, because it wouldn't matter if this area were squished together in the center or distributed out. That doesn't make any difference, right? Its placement this way doesn't matter. What matters is how much of it is this way and its overall thickness. Okay? So, they've asked for the shear here because this will be the maximum shear. We know it will occur there. Again, that's because that's the minimum thickness. So Q is going to decrease as you move out. And notice the thickness eventually increases out here, which will cause the shear to drop farther. But we know that's where it would occur. So the general equation is, let's see, I'm trying to memorize it as well, so let's see if I can do this. IT, and this would be Q. Okay, make a decent Q. So if we're going to calculate the maximum stress, then we better get Q. And Q, we need the particular area times the distance to the centroid of that area, right? So this is going to be a little bit involved because the area we're interested in is that area. That is AP. AP is going to be easy to get, right? It's Y bar that's going to be more difficult. Okay, so let's see if we can figure out AP. What is it? Well, let's see. 1 inch times the length of 4 inches will give us 4 square inches here, 4 square inches here. That's 8 square inches. And then the area up here, let's see, would be 4 more inches times 1. So 4, 4, and 4 would be 12 square inches. Make sense? So AP is 12 square inches. Now we need Y bar. Okay, so how do we get Y bar? Well, you know that let me put a dash line here and here. The centroid of that area and this area occur at the center, right? So if the distance here is 4 inches, this is 3 inches, then this distance is 1.5 inches, okay? And then the centroid line for this area would be just 3 inches plus 1/2 inch, so that's at 3.5 inches, okay? Now probably, you know what, let me break it up the same way, well, I was going to say I could break it up the same way I did the area calculation, but we're here now. We could have broken it up into a 4 inch by 1 inch area like I did before. It doesn't really matter. We'll get the same thing. Okay? So remember, the way that we calculate the average position of the area so that we can find, well, where is the centroid? By the way, let me ask you guys a question. Would the centroid be at 2 inches, 3 inches, or more than 2 inches? What do you think? It can't be at 1.5 inches, right? Because that would neglect this area. Okay. What about 2 inches? Well, 2 inches wouldn't work either because you can imagine breaking it up like this, and the centroid of those two areas would be at 2 inches. Since we still have a little more area, it must be more than 2 inches. So if we get Y bar less than 2 inches, I made a mistake somewhere. Does that make sense? Better get a number bigger than 2 inches. So how do we do it? Well, we add up all the area, and all we do is take the moment of each of the areas and sum them. So the moment of this first area, let's see, let's call this area 1, and let me erase that. This upper area is area 2. Okay, so area 1 multiplied by y1 plus area 2 times y2, except, wait a second, I've got two a1s. Does that make sense? Okay. So let's see, I guess I'll continue this way. So 2 times a1, a1 is the 1 inch by 3 inch, so that's 3 square inches. y1 is the height to the centroid of that area, which we've already decided is 1.5 inches. So there's the area moment of both of these areas. Now I need the area moment of this area. So that would be plus 6 inches times 1 inch would be 6 square inches. And then the height to that line is 3.5 inches. And we've already decided the total area is 12 square inches. Okay? So notice the inches squared will go away and we'll just be left with something in inches, which is what we expect. Why do I have a 2 here and not a 2 there? There's 2 of them, 2 sides. Okay, so rather than adding another term that looks just like that, I just multiplied it by 2. So put this in your calculator, and I hope we get a number bigger than 2 inches. Let's see what we get. See if I can do it in my head while you're doing it. Is it, how much is it? 2.5. Everyone agree with that?
I do.
Okay, thanks. All right, so 2.5 inches is where the centroid of that area is located. So do you see how that's going to be y bar? So let me just put a mark up there. It's supposed to represent the 2.5 inches. Okay. So now 12 square inches multiplied by 2.5 inches is what we need. So calculate Q for me. Well, I can probably do that. 24, 30? Is that right? 30 cubic inches? Because 12 and 12 is 24 plus 6 is 30. Okay. So Q is 30 cubic inches. Now, what shear did they give us? Well, they gave us a shear force in the problem statement of 850 pounds force. So let's plug that in. 850 pounds force times 30 cubic inches. By the way, this thing Q is also called the first area moment, okay, whereas the I that we've been dealing with is more like the second area moment. But anyway, it'll always have units of length cubed. I, speaking of which, we need I for this cross section. So how do we get I? Well, the easy way is to go through the spreadsheet that I made for you guys. So I'll just do that next. Don't feel like doing all the math on the board, so we'll make our lives easier. We'll go back to chapter 6. I made that spreadsheet because I knew it would be very handy to have. And by the way, I don't mind if you use that spreadsheet on exams. I'm not really interested in you calculating area moments. You can draw them in SolidWorks, you can put them into the spreadsheet. I don't care. I would recommend in the professional world, if you ever have to calculate an area moment of inertia, that you draw it in SolidWorks and make sure you don't make a mistake and then let it measure it for you. That's the easiest way to do it. Okay. All right, so let's count. Now, the area moment of inertia, am I going to deal with this particular area or something else?
The entire.
The entire thing. I is always calculated based on the entire area. So let's do that. How will I break it up? Well, I guess I'll break it up into 2 sides and then 2 ends. Okay? So let's see what that looks like. The area, let's start off with the area of the bottom end. That would be just 6 square inches.
Yep.
The distance to the center of that from the bottom would be 1/2 inch. And then also to calculate the area moment of inertia just for that lower part, that would be 1/12 BH cubed, where B is 6 inches. The height is 1 inch, just to be completely correct, I'll say cubed, over 12. Okay? So that's my bottom area. Now I'm going to have 2 of the sides, so let me calculate one and then I'll just copy it again for the other one. That area is going to be a 6-inch length, okay, by 1 inch. So again, that will be 6 square inches. The distance to the center of that area from the bottom will be 4 inches. And then the area moment of inertia would be 1/12 BH cubed, so B is 1 inch. H is 6 inches, which will have to be cubed, and divide by 12. Now, like I said, we've got two sides, so I'll copy this and copy the first. Now, I can't quite copy the first line, can I? Not exactly, almost. What would be different? Y would be different, right? The area is the same, right? Bless you. The moment of inertia, I, for that area about its own centroid is the same, but the distance from the bottom is very different. The distance from the bottom would be 7.5 inches. Okay? Now, our total area moment of inertia is 184, and what would the units be again? Inches to the fourth, good. So from the Excel spreadsheet, we've got 184 inches to the fourth power. How about the thickness? What thickness should I use here? 2 inches, right? Because really we don't care whether this area is touching or not. That doesn't make any difference. Because we're talking about shear out in this plane. Does that make sense? We're not talking about shear on the side here. So anyway, that would be 2 inches of thickness. Okay, so plug that into your calculator, please. Let's see what we come up with. The units will be pounds force per square inch, because we've got inches cubed in the numerator and inches to the fifth in the denominator, which just leaves us with inches squared in the denominator. 850 times 30 over 184 over 2 is how much?
69.29.
Anyone second that? Is that a whole lot of stress? No, not much. Now, of course, I guess it depends on what material you're talking about. If you're talking about a plastic, maybe so. Depending on, foam or something, yeah, maybe that's a lot of stress, I don't know. But for our purposes, that's not a whole lot. Questions, comments? Well, let's work through some more. I want to try something with sort of an odd shape. Let's try 13. Let's see what happens. I guess I should separate these.